Mixtures of gases. So many gas samples are mixtures, not pure substances. So dry air is an example of a mixture of gases. We say dry air because what's the opposite of dry air?
Wet.
Wet air. Okay, so there is wet air. In fact, most air is wet.
Humidity.
Humidity, exactly. So, in fact, this little weather station says the humidity in here right now is 30%. So there is water vapor in the air as well. But just thinking about dry air. Dry air is a mixture of nitrogen, oxygen, argon, carbon dioxide, and then trace amounts of lots of other gases. Like, when your 9-year-old son lets one rip, right? And you're like, whew, what were you eating? What is that you're smelling? It's a gas, right? But then it dissipates, thankfully, unless you're in a really small car with him. That happened. So nitrogen, 78% of the volume of air is nitrogen. 21% is oxygen, 0.9% is argon, and about 0.04% is carbon dioxide. Many times we can think of a gas mixture as being a single gas. Yeah, question?
Going back to the dry air, there was a museum fairly close by here that actually had to have it regulated for dry air because it was all of the artworks were not behind glass or anything like that. The entire building had to be dry air.
Yeah, so regulating humidity can be really important for artwork. Musical instruments do not like dry air, the wooden ones, like guitars. If they're too dry, then they crack and break. And so regulation of humidity is important. And so the water in the air is one of the gas components. Air is a mixture, but we can measure its pressure, volume, and temperature as if it were a pure substance. Because gases behave independently, and they behave in the same way, right? We saw that the molar volume of a gas at STP was 22.4 liters per mole, regardless of what gas it was. So we can still calculate the total moles of gases in the air, even though they're different molecules, and we don't necessarily know which ones they are, because gases behave independently. So the pressure of a single gas in a mixture of gas is called the partial pressure. Because it's not the pressure of the whole thing, it's the pressure of one of the parts, right? So you've got a mixture of gases, maybe 3 different gases. They each exert their own pressure, and it's a partial pressure. The total pressure is all of those put together. So we could look at the pressure due to a single gas. So, pen, come on, give me a pen. We have PV equals nRT. And we could rearrange that and solve for pressure. We get the pressure of that individual gas is equal to the moles of the gas times R times the temperature of the gas divided by the volume. Now, if you have multiple gases in a mixture, they're going to be at the same volume and at the same temperature as all of the other gases. So those are going to be the same, and R is going to be the same. Dalton's law of partial pressures tells us that the total pressure of a gas is just the sum of the pressures from each of the components. And this is a lot like taking, say, a box of fruit, right? I have to write down numbers because otherwise I'll forget. Let's say you have 1 pound of oranges, and you've got 3 pounds of lemons, and 2 pounds of apples. I don't know. What is the mass of fruit in the box? 6 pounds, right? Mass adds, right? So you just have the mass of oranges, the mass of lemons, the mass of apples, you just add them all together, and that gives you the overall mass. Same thing with pressures of gases. Each gas exerts its own pressure, and to get the total pressure, you just add them together. This is the derivation of that. So Dalton's law of partial pressures. The pressure of gas A is equal to the moles of gas A times RT over V. That was just rearranging PV equals nRT. For gas B, again, the RT over V is constant. So we could factor out RT over V, and then what we've got left here is the sum of the moles of the gas. So the total pressure, let's write that in there. So P total is the total number of moles of gas of all kinds times RT over V. The ratio of the partial pressure of a gas component to the total pressure is equal to the mole fraction. So the partial pressure of one of the gases divided by the total pressure. Well, the partial pressure of this gas is its moles times RT over V. The total pressure is the total number of moles times RT over V. And so RT over V cancels out, and we get the moles of A divided by the total number of moles. That's the part divided by the whole. If we multiplied by 100, we'd get a percentage. But if you don't multiply by 100, you have a fraction. So that's the mole fraction. It's the moles of 1 divided by the total moles. And it's given the symbol chi, which looks like a big X. It's a Greek letter. So the mole fraction of A is equal to the number of moles of A divided by the total number of moles. So we can take my pointer that's not working. There we go. Oh, we're back. Okay. PA over P total equals NA over N total. So just copy that down here. So multiply both sides by P total. Now you get PA is equal to X, or chi A, times the P total. So the partial pressure of gas A in a mixture is equal to its mole fraction times the total pressure. So if gas A is 25%, the fraction then would be 0.25. So it's 0.25 out of one of the particles. It's going to exert 0.25 of the total pressure, 1/4. So the partial pressure of a gas in a mixture is the mole fraction multiplied by the total pressure. So the mole fraction is the same as the percent by volume divided by 100. So we learned earlier that air is 78% nitrogen. So if it's 78% nitrogen, then the fraction of air is 0.78, right? So we could find the pressure exerted by nitrogen is 0.78 times the total pressure. So regular pressure at 1 atmosphere, the pressure from nitrogen is 0.78 atmospheres. Let's do an example. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Some chemicals will react with air and sometimes violently. And so you can't just stick them in a jar and put a lid on it because there's air in the jar, right? So what do you do to get the air out? You put something else in. So you put a different gas in there sort of as a blanket to keep the air out. And noble gases work pretty well for that. So chemical engineer puts a mixture of noble gases. It consists of 5.5 grams of helium, 15 grams of neon, 35 grams of krypton. In a piston cylinder assembly at STP, we're asked to calculate the partial pressure of each gas. This is one you're going to have to think about. Well, let's pull out the numbers and see what we've got here. So we've got 5.5 grams of helium, and we've got 15 grams of neon and 35 grams of krypton. So we have a mixture of gases, and so we know that the total pressure will equal the pressure of each gas added together. It's like, well, that's all very nice. We have three variables here. Do we know what the total pressure is? What does STP mean? 1 atmosphere, standard temperature and pressure. So the total pressure is 1 atmosphere. But we still have those three variables. So that's not going to be good enough. But we just learned that the partial pressure of one gas in a component is equal to the mole fraction of that gas times the total pressure. We know what the total pressure is. Could we figure out what the mole fraction of each of these components is? Yeah. It's going to be the moles of, say, helium divided by the total number of moles. We've got masses, but we can do this. We can convert this to moles. So 1 mole of helium weighs 4.003 grams. Periodic table. So 1.3739 moles of helium. This is one of those problems that just gets tedious, is all. We want to convert neon from grams to moles. 20.18 grams is 1 mole for neon. .74331 moles of neon. Krypton's a big guy. 83.80 grams per 1 mole. .41766 moles of krypton. So the total number of moles is just those added together. 0.41766 plus 0.74331 plus 1.3739. Calculator gives me a whole bunch of digits. Here I'm adding, and so when I'm adding, I'm looking for the decimal places. So helium has 2 decimal places, neon and krypton have 3. So my answer will have 2 decimal places. So that's my last significant figure, and then I'm going to copy down 2 extra digits, 4 and an 8. Total number of moles. So the mole fraction for helium is equal to the moles of helium divided by the total number of moles. And the moles cancel out. So this is 0.542. No units on that. Mole fraction for neon, 0.74331 over 2.5348. .29324. What do all the mole fractions have to add up to? 1. Just like percentages of components have to add up to 100%, mole fractions have to add up to 1. So you could calculate the mole fraction of krypton by just subtracting, but I don't know that that's really any easier. 0.41766 over 2.5348. .16477. Just for grins, let's add those up. 0.54201 plus 0.29324 plus 0.16477 equals 1.00002. That's pretty close. Yay, we calculated stuff. Where were we going with this? What were we trying to find? We were trying to find the partial pressure of each gas. I know this happens to me. Sometimes I get into a calculation and then I'm like, oh, wait a minute. What was I doing? So I'm going to erase this up here because it turns out we didn't need that. I've got mole fractions. This is the equation. The partial pressure is the mole fraction times the total pressure. What was the total pressure? 1 atmosphere. So the partial pressure of helium is equal to the mole fraction of helium times P total. So that's 0.54201 times 1 atmosphere. Oh, well, that's just the same as the mole fraction then, right? So there's the pressure of helium. Pressure of neon would be the mole fraction of neon times 1 atmosphere. Now, we don't really need to write that out, do we? It's the mole fraction times 1, so that's going to be 0.293 atmospheres. And then the the partial pressure of krypton, its mole fraction times 1, so 0.165 atmospheres. And if we add those together, they should add up to the total pressure, which they do. Any questions? Yeah?
If we don't know the total pressure because it didn't say STP, how would we go about doing the calculation?
That's a good question. So if they didn't give us the total pressure, how would we do this? Well, they would have to give you some other information. So they might give you the volume and the temperature, and then you could figure out what the pressure was, because you've got moles, you've got the total number of moles of gas. So if you have moles, and you've got temperature and volume, you could calculate the pressure using the ideal gas law, and then stick that in here and apply the mole fraction. Good question. Any other questions? Sample of hydrogen gas is mixed with water vapor. So this is wet gas. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Blech, right? Now let's write this stuff down. Total pressure, so we'll call that PT, is 755 torr. And the water vapor has a partial pressure. So PH2O is 24 torr. And then they gave us a volume, 1.55 liters, and a temperature, 298 Kelvin. And they're asking for moles of hydrogen. I've got a volume and I've got a temperature and I've got some pressure numbers. To calculate the moles of hydrogen gas, I need the partial pressure of hydrogen. I could use the total pressure and calculate the total moles of gas, but that's not what I want. I want the moles of hydrogen gas. So the total pressure, I've got two things here. I've got hydrogen gas and I've got water. So the total pressure is the partial pressure of the hydrogen plus the partial pressure of the water. They each exert a pressure. You add them together, that's the total pressure. So finding the partial pressure of hydrogen here is so simple that it's difficult. 755 equals something plus 24. The partial pressure of hydrogen is the 755 minus the 24. So 731 torr. Okay? So P for the hydrogen, 731 torr. Is that going to be a good unit for the ideal gas law? No, I've got to convert that again. 1 atmosphere over 760 torr. So usually students remember the 760 because we keep using it, right? But sometimes you have a brain fart and you forget, well, which unit does it go with? Does it go with the atmosphere or with the torr? Well, let's think about it. 1 atmosphere, what does that mean? It's 1 atmosphere of gas. That's like regular, right? So let's put 1 with atmosphere. The 760 torr, remember that was a height of a column of mercury. So 760 millimeters of mercury makes sense. 760 atmospheres, that shouldn't make any sense. So if that helps you remember which way they go. Turn on the calculator. 731 divided by 760. 0.98. Nope, not 8. 6. 96184 atmospheres. PV equals nRT. I'm solving for N. I get N is equal to PV over RT. And then it's plug the numbers in. 1.55 liters. Oops. I don't want to confuse anybody. That's not the... Let's do the pressure first. It doesn't matter, but I don't want to be any more confusing than I have to be. temperature, 298. Check the units. Those are working out just fine. So I got my pressure times 1.55 divided by the ideal gas constant divided by the temperature. 0.060966 moles. So when I round this, the 6 makes the 9 round up to a 10. And so I get 0.061, and I need that third place because it's 3 sig figs, so I need to put a 0 there. Moles of hydrogen. Any questions?